In this example, our goal will be to calculate the angular and linear velocity of our object using the work-energy principle of angular motion. So let's suppose that a rod of uniform mass m is held against the wall by a hinge as shown. So we have the following wall, we have the hinge, and we have the uniform rod of mass m that has a length of L. Now, the rod is held horizontally at rest before it is released. We want to calculate the angular velocity and the linear speed at the tip of the rod at the moment the rod reaches a vertical position. Now, we're assuming that L is 1 meter. So our length of the rod is 1 meter. We're holding the rod along a horizontal axis. We let go. The rod begins to rotate about the hinge. Eventually, it reaches the following position, the following vertical position. At the moment it reaches that position, we'd like to calculate the angular velocity and the linear velocity. So our entire problem will deal with the work-energy principle. So because the only force acting on the object is the force of gravity, and gravity in this case is a conservative force, that means the work done on the rod by the force of gravity is equal to the kinetic energy of the object that is gained when it travels this position. So the object loses a certain amount of gravitational potential energy, and that gravitational potential energy that it loses is converted into rotational kinetic energy. So once again, notice the center of mass of the object, which is at the center of the object, moves a vertical distance of L divided by 2. Why? Well, because when the object moves to this vertical position, the distance that it moves is L divided by 2. The distance that the center of mass moves is half of the entire length, L divided by 2. So that means we can use the following equation. So mgh, the amount of gravitational potential energy our object lost when it traveled a vertical displacement of L divided by 2, is equal to mgl divided by 2, where h is simply L divided by 2. And all of this energy is transformed into rotational kinetic energy given by the following equation. I omega squared divided by 2, where omega is our angular velocity that we're looking for. The I is something that we know, it's the moment of inertia. So recall the moment of inertia of a uniform mass m is given by the following equation. 1/3 ml squared, where L is simply our entire length of the rod, of the object. So we simply plug in this entire equation into I, and we get the following result. Notice the L's cancel, so we're left with only one L. Notice the M's cancel, and the 2 on the bottom cancels. This becomes a 3 when we move the 6 over, and we get the following result. So we want to solve for the angular velocity. The angular velocity is squared, so that means at the end we have to take the radical of both sides, and we get the following result. The angular velocity of the object is equal to the square root of 3 multiplied by g, our gravitational constant, multiplied or divided by L, our distance of the entire rod. So we plug in our values. We know g is 9.8 meters per second squared, and we know m, or our L, is simply 1 meter. So we multiply and divide, we take the square root, we get approximately 5.4 radians per second. So this is our angular velocity of the object. To find our velocity, we have to recall that linear velocity is equal to the product of the angular velocity and our length of the rod. So we simply plug in our knowns. We know what the angular velocity is. It's 5.4 radians per second. And we know what the L is. It's 1 meter. So we multiply and we get 5.4 meters per second is the linear velocity of the object when the object's center of mass displaces a vertical distance of L over 2 when the object ends up exactly in the vertical position along our y-axis.